Hey you guys, this is Mr. Millings, and in this video we are going to learn how to calculate the equilibrium constant. And if you remember from an earlier video, we learned how to write equilibrium expressions, right? We said that if you want to write the equilibrium expression for the chemical reaction that we see right here, it's simple. We're going to take KEQ, which is our equilibrium constant, that is to say the relationship between the concentration of the products over the concentration of the reactants. Once equilibrium has been reached, the equilibrium constant is going to equal the concentration of C raised to some sort of power, where C is the coefficient from our balanced chemical equation here, times the concentration of product D raised to the D power, where D is our coefficient that comes in front of the product in our balanced chemical reaction, divided by the concentration of A raised to the A power, where A is the coefficient for reactant A, times the concentration of reactant B raised to the B power, where B is our coefficient that comes in front of this reactant right here. So we learned about equilibrium expressions, and we learned how to write the equilibrium expression for several different chemical reactions. And so in this video, what we are going to do is we are going to focus on the equilibrium constant. We are going to learn how to calculate the equilibrium constant if you know the concentrations of your products and reactants at equilibrium. So let's take a look at our very first example. In this first example, it says the following amounts of each chemical involved in the chemical reaction below are found in a 5-liter container at equilibrium. We have 3.00 moles of SO3 gas. It looks like we have 5.00 moles of O2 gas, and we have 2.50 moles of SO2. So here's our chemical reaction. We notice that they're all gases, and keep in mind that when we're writing an equilibrium expression, we can leave liquids and solids out of our equilibrium expression, but gases get included. And we'll talk about that here in a second. And so what we want to do is calculate the equilibrium constant, or KEQ, for the chemical reaction that's taking place right here. So the very first thing that we have to do here is, in step 1, we need to find the concentrations, or molarity. We need to find the molarity of the substances that are in this chemical reaction. So let's go ahead and do that. If we take a look, what is the concentration of SO3 going to be? Well, to get the concentration of SO3, we need to take the moles of SO3. Remember, molarity equals moles per liter. So we're going to have to take the moles of SO3, which it tells us is 3.00 moles, and then we're going to have to divide this by the volume, right, or the liters of our container, which it says right here is 5.0 or 5.00. And when we put this in our calculator, we're going to end up with 0.600 molar as our concentration for SO3. Let's now find the concentration of O2. If we take a look to figure out the concentration of O2, once again we have to figure out the molarity, and molarity equals moles per liter. We know that we have 5 moles, or 5.00 moles of O2 in a 5.00 liter container, and so when we take this divided by this and use the correct number of sig figs, we will end up with a molarity of 1.00 molar. Let's take a look at our final substance. It says that we have 2.5 moles of SO2. So we have to figure out the concentration of SO2 here. And so once again, we'll take moles divided by liters. We have 2.5 moles of SO2, 2.50 moles, of SO2. And we're going to divide this by 5.00 liters. And when we put this in our calculator and keep the correct number of sig figs, we're going to end up with this concentration. So now that we know the concentrations of each one of these substances, what we now have to do is we now have to write our equilibrium expression. So in step 2, we are going to write our equilibrium expression. And in an earlier video, we learned how to do this, right? We said that KEQ, which is our equilibrium constant, is going to equal the concentration of our products. In this case here, the concentration of our first product, which is SO2, squared, since the coefficient here is a 2, times the concentration of our next product, which is O2, and we have a 1 as the coefficient, so this will be an exponent of 1 here that we don't need to write. And we're going to end up dividing this by the concentration of our reactants. We only have one reactant here, and so the concentration of SO3 squared. And so here is our equilibrium expression. And so keep in mind, whenever you are writing an equilibrium expression, you do not include solids or liquids in your equilibrium expression. You can leave them out, but these were all gases. That's why we've kept them all in here. So now that we know our equilibrium expression, what we can now do is fill in the concentrations that we figured out in step 1. So let's go ahead and do this. Let's go ahead and plug and chug. So we have our equilibrium expression right here. KEQ is going to equal the concentration of SO2. Well, we just figured that out. 0.500 times the concentration of O2, 1.00 molar, to the first power. And this is squared here, just like we did right here. We square it. And we're going to end up dividing this by the concentration of SO3, which we figured out right here, is 0.600 raised to the second power. And so what we can now do is, using these numbers right here, we can solve for KEQ. We can figure out our equilibrium constant for this chemical reaction. So let's go ahead and carry this a step further here. Here on top in the numerator, we are going to end up with 0.25. Molar squared times molar is molar cubed, and over on the denominator side, we're going to end up with 0.600 molar. And typically when we're asked to calculate KEQ, KEQ doesn't really have any units. It's just a comparison between the amount or concentration of products to the concentration of reactants at equilibrium. So we can just go ahead and get rid of these right here. And so if we take 0.25 and we divide this by 0.600 squared, and I forgot to carry down the squared sign or number right here in the exponent, so don't forget to do that. We're going to end up with, when we take 0.250 divided by 0.600 squared, we are going to end up with 0.694. We have 3 sig figs right here. And so this is going to equal our KEQ. So this is our equilibrium constant for this chemical reaction, 0.694. And anytime KEQ is less than 1, which in this case it is, keep in mind that the equilibrium concentration of our reactants here is going to be greater than the equilibrium concentrations of our products over here. So let's take a look at another example. In this second example, it says initially in a 1.75 liter container, there are 4.25 moles of A, 0.507 moles of B, and 0.783 moles of C present. So here's our chemical equilibrium, our chemical reaction right here. Furthermore, it says if 1.18 moles of B are present at equilibrium, we have to determine KEQ. So we're trying to calculate the equilibrium constant. So the first thing that we have to do here in step 1 is determine the concentrations. So let's find the concentrations of our reactants and our products. So if we read closely, it says that we have 4.25 moles of A in a 1.75 liter container initially. So to get the initial concentration of A, we have to figure out the moles per liter, right? That's the molarity of this substance A. So the molarity here is going to equal the number of moles, which is 4.25, divided by the volume of our container, which is 1.75 liters. And when we put this in our calculator, we're going to end up with 2.43. So we have 2.43 molar as our concentration initially of A. Let's figure out the initial concentration of B now. To get the initial concentration of B, we simply take the amount of moles of B, 0.507 moles, and we're going to divide this by the volume of our container, which is 1.75 liters. And when we put this in our calculator, we are going to end up with 0.290 as our initial concentration of B. Let's take a look at the initial concentration of C. To get the initial concentration of C, it looks like we have 0.783 moles, so 0.783 moles divided by the volume of our container, which is 1.75 liters, and we'll end up with a concentration of 0.447 molar, or 0.447 moles per liter. Let's take a look right here. It says if we have 1.8 moles of B present at equilibrium, so it's telling us that the equilibrium concentration of B, so the equilibrium concentration of B is going to be equal to 1.18 moles divided by the volume of our container, which does not change, 1.75. And when we take 1.18 divided by 1.75, we're going to end up with 0.674 moles per liter. So now that we know these concentrations, what we can now do in step 2 is we can make our ice chart, right? And so let's go ahead and copy this chemical reaction down again. This is telling us that 2A is in equilibrium with B plus 2C. And so keep in mind that ice stands for the initial concentration, the change in concentration, and the equilibrium concentration. And so if we take a look here, our initial concentration of A, we just figured out, is 2.43 molar. We'll go ahead and leave off the unit here. We will just assume that it's molar or moles per liter. If we take a look, the initial concentration of B is right here. It's 0.290 molar, and the initial concentration of C is right here. It's 0.447 molar. So now we know the initial concentrations. We're plugging these into the ice chart here. If we take a look, our equilibrium concentration, E stands for equilibrium, and the equilibrium concentration of B is 0.674, 0.674. And so now if we take a look at our mole ratios, or the mole relationships of these different products and reactants, we can see that the ratio is 2 to 1 to 2 right here. And so let's think about this. If this chemical equilibrium is taking place, then right here, as reactants turn into products, we can see that the concentration of B is going to increase by what we'll call X. And if the concentration of B increases by what we call X, then it's going to increase for C by a factor of 2X, since the ratio here is 2 to 1, twice as much C as B. So we'll go ahead and put a plus 2X here. And if we take a look here, when this chemical reaction takes place, the concentration of A is going to decrease So we'll put a negative sign by a factor of 2x. Since the mole ratio of B to A here, or A to B, is 2 to 1, right? And so what we can now do is we can now figure out the change in concentration because we were given this value essentially in the problem. If we can figure out the change in the concentration of B, we can then apply it to this and to this, and we can figure out the equilibrium concentrations of both A and C. So let's go ahead and do that. To get the change in the concentration of B, so to get the change in the concentration of B, we need to take the equilibrium concentration of B minus the initial concentration of B. And so the equilibrium concentration of B is 0.674. The initial concentration of B is 0.290. And when we put this in our calculator, we're going to end up with a change in concentration of 0.384. So X is equal to 0.384. So the concentration of B is going to increase by 0.384 moles per liter, and so the concentration of C is going to increase by 2 times this, so 2 times 0.384, and we'll end up with 0.768. And the concentration of A is going to decrease as reactants turn into products by a factor of 2 times X, which is equal to negative 0.768. And so now that we know these changes here, we can now figure out the equilibrium concentration of A and the equilibrium concentration of C. So let's go ahead and do that now. The initial concentration of A was 2.43. The change is negative 0.768. And so the equilibrium concentration here will be 1.662. If we take a look at the equilibrium concentration of C, we get that by taking the initial concentration of C, which is 0.447, plus 0.768, and we're going to end up with an equilibrium concentration of 1.215. So now that we've completed this ice chart here, what we can now do in step 3 is we can now calculate KEQ. So in step 3, we're going to find what KEQ is, the equilibrium constant. Now that we know the equilibrium concentrations, we can plug them into the equilibrium expression. So the equilibrium expression here is going to be equal to, remember, when we write equilibrium expressions, it's the products over the reactants. So the concentration of B raised to the first power, since there's a coefficient of 1, times the concentration of C raised to the second power, since there's a coefficient of 2 here. And we're going to divide this by the concentration of A, our reactant, and we're going to square that since there's a 2 as a coefficient in front of them. So now we know the equilibrium concentration of B. We just figured that out. The equilibrium concentration of B is 0.674. We know the equilibrium concentration of C. It's right here. It's 1.215. But we're going to square that. And we know the equilibrium concentration of A. The equilibrium concentration of A is 1.662. And we're going to end up squaring that as well. And so when we put this all in our calculator here, we should end up with our equilibrium constant. So let's go ahead and put this in our calculator. And we're going to end up with an equilibrium constant, or a KEQ value, of 0.360. So to recap, initially we found the concentrations of these substances based on the values given in the problem. In step 2, what we did is we used an ice chart to determine the equilibrium concentrations of each substance, and then we plugged those equilibrium concentrations into our equilibrium expression and found KEQ here to be 0.360. So, if you like what you see, go ahead and click that little bomb in the bottom right hand corner, and that will subscribe you to my channel. And feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.